Hi everyone. Today we're going to talk about the fundamental theorem of calculus. And so let me remind you that we've been working with our definition here of our definite integral. So recall our definition has been the integral from 0 to 1 of our function dx equals the limit as n goes to infinity of the summation from k equals 1 to n of f of k over n times 1 over n. Okay, so we've been working with this definition. So let's do one more example. So it's going to be find the definite integral of f of x equals 3x squared minus 4 on the interval 0 to 1. Okay, so typically what I would have you do is substitute it into the summation first and then evaluate the limit. So when you do that, we're going to skip the steps because you have homework on it. And you skip the steps. When you evaluate the limit as n goes to infinity, you get -3. Okay, so this is what I want to investigate here today, because remember our definition, we said we have some function from 0 to 1, and then it gives you the area under the curve. Okay, and we did that by looking at these little rectangles and then adding up the area of the little rectangles. All right, so but what's going on here? Why did we get a negative area? So let's graph this function and then we'll talk about it. So the graph of this function, we got 3x squared minus 4. So it's a parabola facing up, and the vertex is down here at -4. So at -4, and then it is facing up. Okay, so one is around here, and so you're finding this area. Now, if you look at the little rectangles that would be making up our interval here. So here's an example of a little rectangle. Now remember, to find the rectangle, we multiplied by 1 over n for the width, and then the height, it was whatever the y coordinate was. So it's f of k over n. Okay, but then you notice here that f of k over n is negative. With our definition. So when we substitute it in, we get a negative number here for the f of k over n, no matter where we are in our interval. So we got a negative number times 1 over n. Thus, when we add up a bunch of negative numbers, we're going to get a negative number overall. So here we have the integral from 0 to 1 of f of x dx. It equals a negative number, which is okay because that's from our definition. However, if the problem said find the area between f of x and the x-axis, we would just have to make it negative. Well, do the negative of the negative. So then the area would equal technically the negative from 0 to 1 of our function, since it's always negative, since it's always below the x-axis for our interval. And so then that equals negative 3, which is in fact positive 3. So now it makes sense for the area to be positive. Okay, so I'd like to recall we found all these definite integrals in class or in the previous slide. So we go through this process and it takes fairly long. So just like when we used the derivatives, when we had our original definition of the derivative, it was a long process. We used the limit and we had to substitute in a bunch of things. So this process is fairly long also, so potentially we can find some patterns. And that's what Newton figured out. And so he figured out that, well, he actually called it the fundamental theorem of calculus. Let's put it up here on the slide, and then we'll see if our examples agree with the fundamental theorem of calculus. So is there a shorter way to do these things? What is the pattern? And hopefully this will help us. So we got the fundamental theorem of calculus. I don't know about you guys, but once I heard this, I thought, wow, this is pretty powerful stuff because, wow, it's called the fundamental theorem of calculus. It's the main thing of calculus. So here we go. If y equals f of x is continuous on the interval AB, and capital F of x is an antiderivative of little f of x, then the fundamental theorem of calculus says if you integrate your definite integral from a to b of little f of x dx equals whatever the antiderivative is evaluated from a to b, and then that's equals f of b minus capital F of a. There we go. There's our fundamental theorem of calculus. So what I'm going to do is, well, first I should say, let's write out what this notation means. So this means you say f of x evaluated from A to B. So that's how you say it. Okay, so let's do this. Let's see if our work that we did before with our Okay, so this is the fundamental theorem of calculus. I hope I explained it. Not sure what happened with the video. So let's continue on here. I want to see if our integrals that we already figured out, our definite integrals, if they're consistent with the fundamental theorem of calculus. So here we are, the first one, 0 to 1 of x squared dx. You find the antiderivative, so you add 1 to your exponent, multiply by 1 over the new exponent, evaluate it from 0 to 1. you substitute in 1 first, so 1/3 times 1 cubed minus 1/3 times 0 cubed when you substitute in 0. And then when you simplify, we get 1/3 minus 0, which is just 1/3. And there we go. It's consistent with what we found before with our previous definition. Let's substitute in the next one. So 2x cubed this time, dx. We find the antiderivative, so we keep the 2, add 1 to the exponent, divide by the new exponent. We have to evaluate it from 0 to 1, because all our integrals so far go from 0 to 1. We're eventually going to change it. We can simplify the 2/4 to 1/2, substitute in 1, subtract when we substitute in 0, and then once we simplify, we get 1/2. There we go. So we're consistent so far. Let's do the remaining ones. This would be a good time to pause the video just to see if you understand, if you can do it by yourself. Okay, so we go to find the antiderivative. So we add 1 to the exponent, divide by the new exponent, plus, and then the integral of 1 is just x. We have to evaluate it from 0 to 1. We substitute in 1 first. We substitute in 1 first. So we get 3/2 plus 1, and then subtract when we substitute in 0, which is both terms give you 0. And then once you simplify, we get 5/2. Things are looking good. Okay, let's find the last one. Again, you can pause it to see if you get the same thing. 3x squared minus 4 dx. We find the antiderivative, so we get 3x cubed divided by the new exponent. So 3 minus 4x, evaluated from 0 to 1. You substitute in 1 first. The 3's cancel, so you get 1 cubed minus 4 times 1 minus, then it's a good idea to put it in parentheses, so you get 0 minus 0. Once we simplify that, we get -3, which is what we got before. So we can see that the fundamental theorem of calculus is consistent with our definition that we've been using for the integral. All right, so to finish up, well, this is how you can test all your homework problems and find the answers. I would like you, well, let's do some properties.